The discovery of extrasolar planets has certainly heated up in the past few years. With the deployment of the Kepler mission in 2009, several thousands of exoplanet candidates have been discovered and over 2,500 have been confirmed. In many cases, these planets have been gas giants orbiting close to their respective stars, aka hot Jupiters, which has confounded some commonly held notions of how and where planets form. Beyond these massive planets, astronomers also discovered a wide range of planets that range from massive terrestrial planets super-Earths to Neptune-sized giants. In a recent study, an international team astronomers discovered 3 new exoplanets orbiting 3 different stars. These planets are an interesting batch of finds, consisting of 2 hot Saturns and 1 super-Neptune. This study, titled The Discovery of WASP-151b, WASP-153b, WASP-156b Insights on Giant Planet Migration and the Upper Boundary of the Neptunian Desert, recently appeared in the scientific journal Astronomy and Astrophysics. Led by Olivier Dias-de-Mangin, a researcher from the Institute of Astrophysics and Space Science in Portugal, the team used data from the Super-WASP Exoplanet-hunting survey to detect signs of 3 new gas giants. Artists' conception of a Neptune-sized planet with a clear atmosphere, passing across the face of its star. Credit NASA's Exoplanet. The Super Wide-Angle Search for Planets. Super-WASP is an international consortium that uses wide-angle transit photometry to monitor the night sky for transit events. The program relies on robotic observatories located on 2 continents, Super-WASP North, located at the Roque de los Muchachos Observatory in Canary Island, and Super-WASP South, at the South African Astronomical Observatory, near Sutherland, South Africa. From the Super-WASP survey data, Dr. de-Mangin and her colleagues were able to detect 3 transit signals coming from 3 distant stars, WASP-151, WASP-153 and WASP-156. This was then followed by spectroscopic observations performed using the Haute-Provence Observatory in France and the La Silla Observatory in Chile, which allowed the team to confirm the nature of these planets. From this, they determined that WASP-151b and WASP-153b are 2 hot Saturns, meaning they are low-density gas giants with close orbits. They orbit their respective suns, which are both early G-type stars aka yellow dwarfs, like our Sun, with an orbital period of 4.53 and 3.33 days. WASP-156b, meanwhile, is a super-Neptune that orbits a K-type orange dwarf star. As they indicated in their study, WASP-151b and WASP-153b are relatively similar. Their masses of 0.31 and 0.39 mJ and semi-major axes of 0.056 astronomical units and 0.048 astronomical units respectively indicate 2 Saturn-size objects around early G-type stars of V magnitude approximately 12.8. WASP-156b's radius of 0.51 rj suggests a super-Neptune and makes it the smallest planet ever detected by WASP. Its mass of 0.128 mJ is also the 3rd lightest detected by WASP after WASP-139b and WASP-107b. Also interesting is the fact that WASP-156 is a bright MAGV 11.6 K-type star. Number of exoplanets discovered by the Kepler mission as of May 10, 2016, based on their classification. Credit W. Stenzel. NASA aims. Taken together, these planets represent some major opportunities for exoplanet research. As they indicate, these 3 planets also lie close to WASP-151b and WASP-153b or below WASP-156b, the upper boundary of the Neptunian Desert. This refers to the boundary astronomers have observed around stars where short-period Neptune-sized planets are very unlikely to be found. Basically, of all the short-period exoplanets less than 10 days to be discovered so far, the majority have tended to be in the super-Earth or super-Jupiter category. This deficit of Neptune-like planets has been attributed to different mechanisms when it comes to the formation and evolution for hot Jupiters and short-period super-Earths, as well as it being the result of gas-enveloped depletion caused by a star's ultraviolet radiation. So far, only 9 super-Neptunes have been discovered, so this latest discovery, whose characteristics are well known, should provide plenty of opportunities for research. Or as Dr. de-Mangin and her colleagues explain in the study, WASP-156b, being one of the few well-characterized super-Neptunes, will help to constrain the formation of Neptune-sized planets and the transition between gas and ice giants. The estimates of the age of these 3 stars confirms the tendency for some stars to have gyrochronological ages significantly lower than their isochronal ages. Artists' impression of two super-Earths in the same system as a Neptune-sized exoplanet in the Kepler 62 system. Credit David A. Aguilar CFA. The team also offered some possible explanations for the existence of a Neptunian desert based on their findings. For starters, they proposed that a high eccentricity migration could be responsible, where Neptune-sized ice giants form in the outer reaches of a star system and migrate inward over time. They also indicate that their discovery offers compelling evidence that ultraviolet radiation and gas envelope depletion could be a key part of the puzzle. But of course, Dr. Dimanjian and her colleagues indicate that further research will be necessary to confirm their hypothesis, and that further studies are needed to properly constrain the boundaries of the so-called Neptunian desert. They also indicate that future missions like NASA's Transiting Exoplanet Survey satellite and the ESA's Planetary Transits and Oscillations of Stars Plato mission will be vital to these efforts. Obviously, a more thorough analysis is necessary to investigate all the possible implications behind this hypothesis, they conclude. Such an analysis is out of the scope of this paper, but we think that this hypothesis is worth investigating. In this context, a search for long-period companions that might have triggered the high-eccentricity migration or an independent age estimate through asteroseismology with TESS or Plato would be particularly interesting. The sheer number of exoplanets discoveries made in recent decades has allowed astronomers to test and revise commonly held theories about how planetary systems form and evolve. These same discoveries have also helped advance our understanding of how our own solar system came to be. In the end, being able to study a diverse array of planetary systems, which are different stages in their history, is allowing us to create a sort of timeline for cosmic evolution. Further reading: Astronomy and Astrophysics. Exoplanets featured hot Jupiter, hot Saturn, Neptunian desert, super Neptune, super WASP,